So today what we'd like to review is gas laws. And in gas laws, it can be complicated, but it really is distilled down to an equation, PV equals nRT. And what I want to do today is help you understand that equation so you can use it in the different type of problems that you see in chapter 8. So let me just go ahead and get my other computer set up so I can see what I'm talking about. What I would like to do first is just talk to you guys about gases and how we describe gases. There's actually 3 lecture notes on this material. Let me just show you this on Canvas so that you guys can see what I'm talking about. So when you go to chapter 8, which is where we are now, okay. Gases are the most erratic, but yet they're the most understood in terms of the 3 phases. So gases, make sure you guys understand the kinetic molecular theory. And the kinetic molecular theory simply states the behavior of gases. And I think this happens to be it over here. Just see real quick. Okay. So you can see here on the right side, you open that up, that there are 3 phases of matter: the solid, liquid, and gas. And gas probably is the greatest in the amount of quantity. And we actually live in a sea of gas. If you look directly overhead, if you're outside, you're being crushed by all the gases overhead. Remember that matter has mass, and even if it's a gas particle, which seems to just float around, like if you have some smoke, it seems to float around, that's made out of matter. And the gases are basically being attracted to the Earth's surface through gravity. Just like water. If you have water and you pour it in the ocean, it'll be there. But because it is an environment where there's other water molecules there, it will seem to hover, but actually gravity is pulling it down as well. So gases will seem to like swim in our atmosphere, but that's because it's in a sea of gases. It'll actually be attracted to the gravitational pull, but because it's with other gases, it's going to seem to hover around. But the molecules directly over your head is what's causing atmospheric pressure. Okay, it's causing atmospheric pressure. So atmospheric pressure, you guys know, is the pressure that you guys that pressure is reduced when you go to higher elevation. Why? Because there's less gas overhead. So there's less molecules pushing on you. So atmospheric pressure is an indicator of how much gas you have overhead. It's why when you have a storm and you have a low pressure system, what's going on basically with a storm is that you have a void of gases in a region, and then the other gases seems to get sucked into that void. And so that's where the storm seems to head in terms of filling in that void. And then, of course, when you have a storm, you get rain and all that. But this, what you see right down here on the right, is actually what we call isobestic lines, and it shows you the region in which you have regions of similar pressure, but at each contour, that's the lines, you're going to see different type of pressure. So pressure is one of the ways we can describe gases. The other, of course, is the volume. How much, what space does it occupy? Now, in the atmosphere, it's just free to roam because it's not held by any container. But if you blow a balloon up. Now it's housed in a container. That's the volume. And then the last variable, well, the second to the last variable would be the temperature. Temperature monitors molecular motion. So temperatures will monitor the motion of the gas. The faster the gas moves, the higher the temperature. The slower the gas moves, the lower the temperature. Problem with gas is that if you slow the gas movement low enough, then it starts, intermolecular forces comes into play, and then they stick to each other. Then it's not a gas anymore. What you will see is that there was a scientist called Charles who indicated that if you took the gas and you reduced the temperature and you didn't account for the stickiness, intermolecular force, so that it condensed to a liquid and then eventually a solid, but just extrapolate, do a theoretical extrapolation, then you can get to a point where there is zero volume. And he indicated that the temperature would be where everything was perfect. And that was actually calculated at minus 273.15 degrees Celsius. And we call that today absolute zero, 0 Kelvin. And then the last variable that you should understand is the amount of gas. When you blow in a balloon, there's only a certain amount of air that you can put in there. That's the amount of gas. And we indicate amount of matter by Avogadro's number, the moles. Okay, so that's what you see right here in terms of kinetic molecular theory. The kinetic molecular theory simply tells you that we can assume that gas particles very small. Okay, well, at the atomic level, molecular level, yeah, it's very small, but it's small compared to the distance that separates them. Even when we compress a gas, like in your tires, they're still separated by a large amount of distance, okay, because it's in gas phase. So that's one of the assumptions. The other assumption is that they are constantly moving. And what will happen is that they will eventually, occasionally, hit each other. And when they hit each other, it's perfectly elastic. What that means is that they just bounce each other. They don't stick, okay? It's an elastic collision, and they're moving further apart. So it's in random motion. They hit the boundary, like in in the balloon or your car tires, and that's results of pressure. Pressure is nothing more than force per unit area. So when it's pushing on the sides of your tire or the side of the balloon, it hits it with a certain amount of force. And because the gas are so small, they have a force per unit area. But because you got so many gases hitting it at the same time, the force per cumulative area is substantially large when you put a large amount of gas, and that results in the pressure. That results in the expansion, okay? Gas particles do not repel or attract each other. I already talked to you guys about that, the collisions between them. The contact between them is perfectly elastic, and then their molecular motion is monitored by their absolute temperature, okay? That would be the Kelvin. So we can think of gases in terms of this model, where if you've played pool or billiard and you see the billiard balls on the table and you use the cue ball to hit one ball, then they supposedly transfer the energy and they stay within that container. Well, gas, instead of balls being static, are constantly moving, like in the second diagram right here. Okay, they're constantly moving, and when they hit the sides, that's the pressure. The size of the container is the volume, and the how fast they move is the temperature. The amount that is in there is the moles. And so this might be a better depiction right here. This might be a better depiction right here in terms of describing a gas. Have you ever driven up in elevation? Like maybe you're driving up to Big Bear or Mammoth Lakes, or even going back east and going up to Denver. If you have a bag of chips, okay, and it's perfectly enclosed, it hasn't been open, it'll look bloated like in this movie. And the reason why that happens is because when the bag was closed, it was closed at sea level. So the pressure inside when it was closed is equal to the pressure outside. What happens when you go up in elevation is that the pressure starts to decrease. Why? Because I told you the amount of air overhead, there's less. So there's less pushing down on you. It's a lower pressure. So when you go up in elevation, what will happen is that the pressure inside is still at a certain pressure. Pressure outside is lower. So they want to equilibrate. They want to be the same. So of course, in order for the pressure to decrease inside, the volume has to increase. Okay. There's an inverse relationship between volume and pressure. To make the pressure decrease so that it's the same outside, the volume has to increase. Well, that's what you see right here. That's what you see right here. So this right here is a movie. And here you can see this person driving up in elevation, and boom, there it goes. The bag of potato chip burst open. Okay. So that's one of the things that you guys actually do when you go diving. If you've ever taken, if you've been certified and you go diving, one of the, and I've been certified when I was in grad school, but one of the rules they tell you to do is that in your ascent, you need to constantly breathe through your BC, your breathing apparatus. Okay. And the reason why is because if you're like 100 feet down, okay, or even 200 feet down, and you hold your breath, then your lungs have a capacity to hold a certain amount of air that you're breathing through your tank. And the pressure in your lungs is equal to the pressure outside in the environment, the elevation that you are in when you dive. Now, the pressure that you feel at 200 feet is going to be equal to the column of water overhead, okay? And that's a lot of water. As you go up and make the ascent, there's less water overhead, so the pressure decreases. What happens to your lungs if you hold your breath? The pressure in your lungs is still going to feel this, still going to have the same pressure at the 200 feet level. When you get to 100 feet, now what does the pressure in your lungs want to do? It wants to be equal to the pressure outside. In order for that to happen, it has to expand. That means that your lungs have to expand in the volume. It gets to the point where the tissues in your lungs can't hold the gas anymore, and it'll rupture, it'll break. Okay, so in order to prevent that, you need to constantly breathe as you make your ascent so that the pressure in your lungs equilibrate with the pressure at the elevation while you make your ascent. Then there's the other problem that you have is that the solubility of matter decreases with pressure. Okay, the solubility of gas decreases over pressure. So at 200, the solubility of oxygen, nitrogen will go into your blood. As you go up in elevation, that solubility decreases and the gas starts coming out of your blood. The problem with that is that it doesn't come out as very nicely as if you were breathing in. When it comes out, it bubbles, just like when you open a soda bottle and you see it fizz. Well, it's fizzing in your blood. Okay, and that means that your blood can't be transported from your lungs where it needs to be oxygenated to the vital tissues, and that results in what we call the bends. And so what deep sea divers need to do is they need to go up in elevation and then stay there for a while. That way the gas that is in the blood slowly comes out and it doesn't bubble. It just slowly leaks out, and then it's okay. You have the right amount of solubility for that pressure, and then you go up again at a different elevation and you stay there. So that's what deep sea divers do. Okay, anyway, enough about that. What I do want to talk to you guys about is the gas laws. And what you see right here are 4 gas laws. And you can go through the slides right here. It talks about Boyle's law. It talks about Charles' law. It talks about this guy called Avogadro's law. And there's also one more that I don't put in here. It's Guy-Lussac's law right here. Guy, G-A-Y is not gay, it's Guy. Lussac is one person. He was a French person, okay? But let me describe Boyle's law. And let me describe it in terms of what you already know. If you are in San Diego and you have a balloon, the balloon will have a certain size, okay? And then suppose you take that balloon and you're able to transport to Denver, where it's a mile high. What happens is that in San Diego at sea level, you have a certain amount of pressure. Let's say it's 1 atmospheric pressure, because at sea level, that's generally 1 atmosphere. Well, as you go to elevation, the pressure becomes lower. Let's say it happens to be 0.7 atmosphere. Okay, 0.7 atmosphere. We measure pressure in terms of atmosphere, millimeters of mercury, torrs, 80 pounds per square inch. All these are units of pressure. But ATM is what scientists like to use, atmosphere. Well, when the pressure gets larger, when the pressure is reduced, what happens is that the balloon expands, okay? The balloon expands when there's lower pressure. And that's because the pressure inside wants to equal the pressure outside. And the only way it can do that is occupy more space. That way it's hitting the side of the wall with equal intensity as if it were that atmosphere. What I'm trying to say here is that there is a inverse relationship between pressure and volume. The higher the pressure, the smaller the volume. Okay, the lower the pressure, the higher the volume. So that, in a nutshell, is Boyle's law. Boyle's law. Charles' law, which I talked to you guys about briefly, tells you that, and again, you can do the experiment. You have a balloon, and what happens is that, why are we using balloon? Because balloon has variable temperature. The temperature can vary. So we have a balloon, you're inside your house, it's in winter outside, it's snowing, it's really cold. And when you blow up that balloon, it has a certain size. Now you go outside, or maybe you stick that balloon in the freezer. But if you go outside and the temperature is like -5 degrees Celsius, inside your house, it's about 20 degrees Celsius. But let's say we go outside, it's 5 degrees Celsius. The molecules are now moving slower, which means that it's going to collide with the wall less often, which means that the volume is going to be smaller, because again, you want the pressure to be constant. The pressure inside the house has to be equal to the pressure outside. So for that to happen, the volume of the balloon needs to get smaller. And you can see that if you take a balloon, stick it in the freezer, it starts to collapse. So what does Charles' law give you? It tells you that the volume and the temperature are directly proportional. The lower the temperature, like if you go in your house to the outside, the smaller the volume. The balloon goes from its normal size to collapse size. So it tells you there's a direct relationship between the two. The higher the temperature, the higher the volume. Okay, because we're looking at temperature as the independent variable here. So that's Charles' law. It basically tells you right here, this one right here, tells you that the volume and the temperature are directly proportional to each other. Guy's law just simply tells you, this is Guy-Lussac right here. It simply tells you that there's a direct relationship between pressure and temperature. And that makes sense. If you ever pressure and temperature, if you have a soda can, okay, there's certain, the carbon dioxide is dissolved in your soda can, but there's a certain amount of gas outside. Let's say you have beverage and it hasn't been opened, there's a certain void space outside the liquid. There's gas there. So you stick that soda can in the trunk of your car. And in a summer's day where it might be like 98 outside, in the trunk of your car, it can go as high as about 130, 140. Pressure really goes up. What happens is that gas will start to move faster, but it's in a container that is fixed. It won't expand. But because the temperature is higher, it's the molecules are moving faster. It's going to hit the side of the container more often. It causes that pressure to increase. Eventually, the pressure will be so high that the structure of the can can't withstand it, and then it'll burst on you. So again, that's Gay-Lussac's law. It's easy to envision that the higher the temperature, the higher the pressure. That's what this tells you right here. Okay, the higher the pressure, the temperature, the higher the pressure. Now, each of these gas laws right here, if you're looking at Boyle's law and you're looking at pressure volume, then that means that the number of the temperature doesn't change and the amount of gas doesn't change. If you're looking at Charles' law, that means that the pressure doesn't change and the moles doesn't change. So there are 4 variables that we talked about. When you're looking at these gas laws, they only investigate 2 of the variables. That means that the other 2 are not going to affect the composition of the gas. That means that before and after, when the temperature goes up, the other 2 variables stays constant. So when the variable stays constant, let's say we have a balloon and we have 1 mole of gas in a balloon and we go from San Diego to Denver. Well, that 1 mole of gas in San Diego is still 1 mole of gas in Denver. So we say delta N, N stands for moles, delta stands for change, is 0. So the moles after minus the moles before equals 0. So delta N is equal to 0. It doesn't change. The last gas law that I want to talk to you guys about is Avogadro's law. Avogadro's pretty simple. The more gas you have, the higher the volume. Makes sense. If you take a balloon, you blow it up, you're putting in more gas in a balloon, the balloon's going to get larger, okay? And we're holding the pressure and the temperature constant. So these are your gas laws. These are your gas laws. These are Boyle, Charles, Guy, Avogadro. It's easy to relate to based on our everyday experience, okay? But rather than think about all these gas laws separately, you can actually think about, here's again the summary of the gas laws. You can actually think of the gas laws as combining them, okay? And when you combine them, you can see that volume is directly proportional to the moles. The higher the amount of gas, the greater the volume. Volume is directly proportional to the temperature. The higher the temperature, the greater the volume. But it's inversely proportional to pressure. The higher the pressure, the smaller the volume. So when we do that, we say if we want to put it in a math equation, then we need to put constants. Constants are just number that doesn't change. And this constant that we use, we call R. And R is called the universal gas law constant. And what we have right here is the equation that all the gas laws distill to. In fact, all you need to remember is this particular gas law. It's called the ideal gas law, okay? Because the ideal gas law will always break down to one of the 4 gas laws. Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. Why? Because when you're looking at Boyle's law, then the pressure and when you're looking at Boyle's law, the temperature and the moles are constant. So that doesn't play in the role. And so when you take this PV equals nRT and you basically say that temperature and moles are constant, you get the relationship that pressure is inversely proportional to the volume. Anyway, when you're using PV equals nRT, you got to make sure that your volume is in liters, that your temperature, well, even if you're not using PV equals nRT, but your temperature should always be in Kelvin. Your pressure should be in atmosphere. Okay, ATM is the abbreviation. And of course, the amount is always expressed in moles. That's a must. And when you use those units, okay, then that value, that constant, R, the universal gas law constant, is 0.08206. 0.08206. So you need to memorize this number when you do PV equals nRT. A lot of books will just write 0.0821. That's fine too. I just learned it as 0.08206. Okay, so 0.0821 liters atmosphere, moles Kelvin. Those are the units. Notice that liters and atmospheres are on top. Why? Because liters, atmosphere is going to be right here. Liters is right here, and atmosphere is right here. So they have to be on top in order for the units to cancel, and then moles and kelvins are in the bottom, because moles and kelvins in the gas laws are in the numerator. And if you want the unit to cancel, then that unit in the R needs to be in the denominator. Anyway, please remember PV equals nRT, because that's the equation that you will use and what we will be talking about in the next slide. Okay, PV equals nRT. So again, this is the derivation of the ideal gas laws. There's two types of gas law problems, and I like to call this condition 1 and condition 2 problems. Condition 1 is when you have a situation like a balloon at sea level. You can describe the parameters of the gases. You can say, oh yeah, that the volume of that gas is 1 liter, the pressure is 1 atmosphere. I have 1 mole of gas. You can calculate temperature of that gas using PV equals nRT. Why? Because in PV equals nRT, you already define the pressure, the volume, and the moles. So you can use PV equals nRT to figure out the temperature. That's a condition 1 where you're just trying to define the variables for the gas under one condition. Whether it be here in San Diego, you're not changing, say, the volume, for example. You're just trying to define what one of the variables in PV equals nRT. You're not taking that gas system from one place to the other. So the variable change. The variable doesn't change it under condition 1. So that's one type of problem. Okay, straightforward, plug and play in terms of the ideal gas law. You want to use that. Then there's condition 2. Well, there's the second condition, condition 1, condition 2. So this is what I want to define in terms of condition 1, condition 2. Here is condition 1. And let's say this is condition 2. And let's just say, for the sake of argument, for what we've already talked about, the only difference between these two conditions is the pressure. Delta P does not equal 0. In other words, there's a pressure change. So you have this condition where you have a balloon here, and over here, the pressure is going to be lower at higher elevation. You guys know that at higher elevation, the size gets larger. So that's condition 1, condition 2, where one of the variables, or maybe more of the variables, will change. It's not constant. To solve this problem, you need to know a little bit of algebra. Okay, so I'm going to break off and do a little bit of review on algebra. So here's the review. If in gas laws, yeah, you can solve it using dimensional analysis, but it's best approach using algebra, okay? Proportions. So this is a review on math. Let's say we have a number, a fraction, AB. This could be like 12 over 5 or 30 over 3, okay? We have a number. Let me give you an example, like 20 over 11, okay? And that is equal to another number, but it's a fraction. And let's say that that ratio right there is equal to like 40 over 66. Oh, sorry, not 40 over 66, but 40 over 22. Let me clear that. 20 over 11 equals 40 over 22. So this is A over B equals C over D. Now, when you do algebra and you want to isolate the variable, when you isolate the variable, that variable has to be over 1. And all the other variables, in this particular case, B, C, and D, has to be across the equality. Okay, so if we want to isolate A, what we usually do is we multiply both sides by B. That way B is canceled. And we get this equation, A over 1, because any number over 1 is just that number, okay, is equal to C over D times B, okay, over 1, or is equal to C times B over D. That's A. That's isolating the variable. That's isolating the variable. Suppose we want to solve for D in this case. If we want to solve for D, then this is what you would do. You would first multiply both sides by D, okay? And that gets the D variable to the numerator. Numerator's on top. Numerator's on top. Denominator's on the bottom. So you need to get that variable in the numerator. So what this does is that the D cancels. And then what you need to do is you need to isolate D so that it's alone. So what you can do is divide by A and multiply by B. That way the A's cancel, but you have to do that in both sides. You need to divide by A and multiply by B. And what you get is D over 1 is equal to C times B over A. Okay, that's what you do that's what they would have taught you in math, in your math class, in terms of dealing with fractions. What I want to show you is the shortcut. And the shortcut is the following. When you have ratios like this, then the quick and dirty way of doing this algebra is that whenever you move a variable across the equality sign, this is the equality sign, it has to go across an opposite. So B needs to go to the numerator when it goes to the across the equal sign. A needs to go to the denominator when it goes to the equal sign. D here needs to go to the numerator. C needs to go to the denominator. In other words, that's how these things are going to vary. So let me do this again so that you can see this. Why is this so important? Because you guys are going to be doing this a lot in gas laws. So let's say I want to isolate B, A, which was our first example. What I want to do is move B here, and I'm done. If I move the B there, remember, it's going to go from the denominator to the numerator. When it goes across the equality sign, we have A is equal to C times B all over D. Okay. It's the same as multiplying both sides by B, except it's a quick and dirty shortcut. Suppose we want to isolate D. Okay, then we need to move D over here, send A down here and B over there. When we do that, what we get is this right here. Oops. Yeah. So B is going to be next to C, and then A will be down here. And isn't this the equation that we derived in the previous example? So again, you want to do quick work of the variables. One last example, A over B equals C over D. Let's say I want to isolate C in this case. Well, isolating C requires D to move over there. C is equal to A times D all over B. Okay, so use this and quick and dirty shortcut in order to make it easier on you to manipulate the ideal gas law. So we had an example, 20 over 11 is equal to 40 over 22. Okay, if we do that, we want to isolate 20, then what we would do is send 11 over here. So 20 is equal to 40 times 11 over 22. Okay, so this right here will just be 11, and 11 over 22, what we would get here is that, oops, that would be 2, I mean. 11 divided by 22, that's 2. 40 divided by 2 is just 20. So you can see how that works. Okay, use that shortcut. Use that shortcut when you're doing this. So let's go back to what we've been talking about. Condition 1, condition 2. This will be relevant when I start doing problems. Okay, that's this right here. When you have the ideal gas laws at sea level, well, when you have a gas at sea level, it's going to obey the ideal gas law. Okay, PV equals nRT. You take that same system, that balloon, and you go to Denver, it's still going to obey ideal gas law. This is condition 2. But remember that in Denver, this particular example, we say the temperature is constant and we say the moles hasn't changed. So that's going to cause these guys to cancel out in the equation. R is also going to cancel out because it's constant. So what you have is P1 V1 over P2 V2 equals 1. When things cancel, they don't go to 0. They equal 1. So this is equal to P1 V1 equals P2 V2. That right there is nothing more than Boyle's law. So when you have condition 1 on top of an equation and condition 2 in the bottom, and the variables are constant, then they cancel out. Okay, and you get back the original gas law problems intended for that condition. Anyway, keep that in mind so that it makes the math easier for you. Let's move on. So this is a condition 1 problem. How many moles? So we have moles. That's the question. Are in 2 liters. 0 degrees. Remember, the temperature always have to be in Kelvin. So that's 273 Kelvin. Always change your temperature to Kelvin if you're dealing with gas laws. And pressure equals 1 atmosphere. So this is pretty straightforward. What you want to do is you want to use PV equals nRT. That's over 1. We're solving for moles. So we send RT down here. N equals PV over RT. That's our equation that we're going to use to solve for moles. Again, we're doing that technique that I showed you above. Any variable or number alone is just over 1. So I'm making this a fraction for you to show you that you need to move RT to the denominator across the equality sign. So now we can solve for moles, and moles is the moles of gas is just equal to 1 atmosphere times 2 liters. That's the pressure and the volume, all over R, 0.08206 liters, atmosphere, mole, Kelvin, and the temperature is 273. The kelvins will cancel. The moles, because it's in the denominator of a denominator, now goes up to the numerator. The liters will cancel and the atmosphere will cancel. What we get is moles as the proper unit when we do this math. So what does the math look like? It looks like this. Okay, let me clear this out. That's the setup. And you get a number of 8.93 times 10 minus 2. Pretty straightforward. Just plug in the values in PV equals nRT. Okay, just plug it in because it's a condition 1 problem. The variables don't change. It's condition 1. Here's another example. Hydrogen gas occupies 2.33 liters. So that right there happens to be the volume. 745 torr is the pressure. 27 degrees Celsius is the temperature. What is the new pressure? Well, this is the new pressure. So we're looking at pressure 2. This is a condition 1, condition 2 problem. Why? Because you have one pressure at 745 torr, and now you're trying to figure out the second pressure. Whenever you have 2 variables that are in the problem, that's a condition 1, condition 2 problem. It's going to require the combined gas laws situation. When what I showed you for condition 2, that's called the combined gas law. If the volume is decreased, now the volume is changed. This is V2, this is V1, and the temperature is, this is T2. That was T1. So the first thing that you need to do in these is set it up. P1 V1 equals nRT1. Okay. This is the combined gas law. P2V2 equals N2RT2. And we can do this because under the first condition, it's going to obey the ideal gas law. Under the second condition, it's going to obey the ideal gas law. So that's what we are doing right here. Now, the volumes are going to be volume 1 equals 2.33 liters. Volume 2 equals 1.22 liters. Temperature 1 equals 27 degrees Celsius. You need to convert that to Kelvin right away. So add 273 to this, that's 300 Kelvin. Temperature 2 is 100 degrees Celsius, that's 373 Kelvin. Always, always, always convert your temperature to Kelvin, no matter what, no matter what. Your pressure 1 equals 745 torrs, and pressure 2 is what you guys are going to be solving. Okay, now you can convert torrs to atmosphere. This is the conversion factor. 760 torrs equals 1 atmosphere. 760 torrs is also equal to 760 millimeters of mercury. Okay, so this is, sorry. Millimeters of mercury, right there. mmHg, millimeters of mercury. Those are different units of pressure. Okay, so we can convert this to atmosphere. But what you guys are going to recognize is that you only use atmosphere and liters if you're using R. Always use Kelvin though. Always use Kelvin. And here's the reason why you don't necessarily need to convert 745 to atmosphere. Here's the reason why. Look at this equation right here. It's condition 1, condition 2. You guys are going to be solving for this variable right here. Right there. Let's clean it up. We know that the moles are not mentioned in this problem, so it's going to cancel. 3 moles over 3 moles is just 1, so it's going to cancel. R is going to cancel. Okay, so this equation simplifies to the following. P1, change this. P1 V1 equals T1 P2 V2 over T2. Notice you're not using R anymore. If you're not using R, then you're not, you don't have to use atmosphere. You can use torr. You don't have to use liters. You can use milliliters, but they have to be the same units for both situations. So if I'm using milliliters here, I have to use milliliters here. If I'm using torrs here, I need to use torrs there, but it doesn't have to be atmosphere. Temperature is always in Kelvin. I can't stress that enough. It always has to be Kelvin. So here's what we do. Remember, we're trying to solve for P2 because that's what the problem is. What's the new pressure? So we go into our bag of tricks and we solve for this. And when we solve for this, this goes upstairs, this goes down, and this goes up. So when we do that, this is the equation we get. P1, V1, and V2 still stays the same, but now T2 is going to be up here and T1 is going to be down there. That's the equation that we're going to be using in our problem, okay? It's the combined gas law. It's a condition 1, condition 2. All we've got to do is plug in P1 in here, V1 in here, T2 here, V2 here, and T1 there. All we got to do is plug that in, punch it in our calculator, and we get the new pressure. So let me show you how that goes. Okay, let me show you how that goes. So will the pressure go up or down? First of all, always try and look at the problem and think about, based on your experience, are you going to get an answer that is higher than 745 or lower than 745? Now, think about this. The volume goes from 2.33 to 1.22. So what you're doing is the volume is decreasing. It's becoming smaller. When you have smaller volume, the pressure goes up. Then the temperature goes from 27 to 100. You're increasing the temperature. So the temperature goes from lower to higher. Both instances is showing you that the pressure has to go up. So your answer, P2, should be greater than 745. Okay, torr. Again, as an indicator to you that based on your common sense, where your answer should be, it's going to be greater than 745. Okay, so keep that in mind. So let's take a look at how to solve this problem. Okay, this might be a drawing that you could do. The drawing's not important. It just shows you what's going on. Here's the temperature at 27. The new temperature now is 100 degrees. The volume is 2.33. The new volume is 1.22. What happens to the pressure? The pressure should increase. Okay, here's the equation that I showed you about. The n's and the r's cancel. You get that, and this is exactly the same equation that I wrote in the previous slide. All we got to do now is plug it in. Notice I'm using torrs rather than atmosphere. Notice that the liters will cancel, the kelvins will cancel, and when I do the math, I get my answers as 1770 torr. Now, if the question is, what is the new pressure in the atmosphere? Then simply take this 1770 torrs. And remember that for every 760 torrs, you have 1 atmosphere. And you can do that conversion factor. And that answer is 2.33 atmosphere. You can, as the last step, you can convert the torrs to atmosphere. Okay. So that'll save you time. This is a condition 1, condition 2 problem. Condition 1, condition 2 problem, always start with this. This is what we call the combined gas laws. Of course, the R's are going to cancel. That's automatic. That's automatic. So you can actually start with this. P1 V1 equals NT1, P2 V2 equals N2 T2. Why? Because the R's will cancel. But because I asked you to remember PV equals nRT, because I asked you to remember PV equals nRT, which is the only equation you really need, that's why we have it here. Okay. So that's a gas law. Here's another problem. This is it seems like it's a Boyle's law problem, but again, let me show you how we attack this problem using the combined gas laws. You have a 6.5 liter sample of oxygen at 24 degrees underwater at 6.5 liters sample of gas. So the volume here is 6.50 liters. And the temperature is 24. Add 273 to that. So you get a temperature of 303 Kelvin. Always change your temperature to Kelvin. And then the pressure here is 1.5 atmosphere. If the balloon is moved to a lower depth so that the pressure here is 2.50, what is the new volume? If the temperature is not mentioned, again, or the variable is not mentioned at all, assume that the temperature is zero. The change in temperature is zero. The change in moles is zero because it's never mentioned. When you're just looking at pressure, volume, and the moles and the temperature is constant, that's Boyle's law. So here's what happens, okay? Basically doing that, you should see that the pressure that we calculate, the new pressure we calculate should be, or we're calculating the volume. The new volume that we calculate should be smaller. It makes sense. You're going to a place of greater pressure. Okay, so here it is. Here's the combined, everything cancels out. This now equals 1 over 1. We bring this to the numerator. What we get is P1 V1 equals P2 V2, which is what you see right here. And what we are doing? We're solving for V2. So send P2 down here. And that's the equation we have. Let me clean this up for you. Okay, that's the equation we have. All you got to do now is plug in the variables, and you've got your answer. The hardest part is making sure you understand the algebra so you can manipulate the PV, N, and T variables. If you can do that, these problems are super easy. Okay. Here's another problem. Okay. Again, when you start a problem, organize your thoughts, organize your work. A gas occupies 2.22 liters, so that's a volume. The temperature is 0 degrees Celsius, so that's 273. Write it down on your piece of paper. To what temperature? That's the question mark. Must the sample be heated if it's to occupy? This is a Charles law problem. All you see here is volume and temperature. But we're not going to use it. We're not going to approach it using Charles' law. We're going to approach it using condition 1, condition 2. And that's this right here. What are we solving for? What is the new temperature? So this is the variable we are solving for. Remember, the moles are not mentioned. The moles are canceled. R is automatically going to cancel. And the pressure is not mentioned. So that's going to cancel. So what you have here is V1 equals T1 V2 over T2. Remember the algebra I showed you? T2 is what we need. It needs to go up in the numerator. V2 goes up here and V1 goes down here. So T2 is going to be equal to T1. T1 stays the same place. V2 over V1. The shortcut that I showed you is going to play a vital role in the ideal gas law. And this is what you see right here. Okay, this equation and this equation are the same. All you got to do now is plug in these values. This is 273 Kelvin. 0 degrees Celsius, 273. Always convert temperature. I can't say that enough time. I'm going to keep saying it because you guys are going to forget. Always convert Kelvin, temperature to Kelvin. V2 is the second one, 3.22, and V1 is 2.22. So when we do that, we have this, and now you can solve the temperature. It's 396 Kelvin. If you want it in Celsius, subtract 273 from that, 123. Okay. If you had put 0 degrees here, it wouldn't work because anything over 0 is just 0. You won't be able to solve that problem. You got to convert it to Kelvin. Got to convert it to Kelvin, always. I want to introduce a new variable, a new condition here. It's called STP, standard temperature and pressure. A lot of times we do experiments, and we're going to be doing the experiments, say, not in a laboratory A, but in a laboratory X. But we want to mimic the results from laboratory A. But maybe we don't have the right conditions. So we need to agree as a scientific community under what are standard conditions. Well, that's what STP is, standard temperature and pressure. And it's defined as 0 degrees Celsius and 1 atmosphere of pressure. So if you want to carry out a reaction or an experiment, and you want to do it under the same conditions as, say, lab C, and they do it at STP, then you know right away. They did it at 0 degrees Celsius, 273 Kelvin, and 1 atmospheric pressure. That's what they did. And when you do that, let's go back to PV equals nRT. This is 1 atmosphere. This is 273. This is always 0.08206. You can solve for V and N. Let's say we have V, and we have this right here. Let's assume that we have 1 mole of gas. Let's just say, okay, we have 1 mole of gas. How much will it, what volume will it occupy? Well, nRT over P. If we solve this for 1 mole of gas, T is 273, P is 1 atmosphere. Find out that that 1 mole of gas will occupy 22.4 liters. Plug it in, you get 22.4 liters. So now at STP, we can use that as a conversion factor. For every 1 mole of gas, that 1 mole of gas will occupy 22.4 liters. We can use that because our pressure and our temperature are assumed to be this value constant. Okay, so here it is right here, 22.4, 1 mole of gas, STP. Now, what I will do is I won't tell you that the condition is STP. What I will do is I say, okay, here's a problem. You've got 760 torrs, and you've got, say, 0 degrees Celsius. Right away, you should recognize 760 torrs is 1 atmosphere. That's STP conditions. Okay, that's STP conditions. Or maybe I'll tell you, okay, you have 273 Kelvin, and you've got, say, 14.6 psi. 14.6 psi is 760 torrs. 760 torrs is 1 atmosphere. That's STP. Okay, that's STP. So sometimes I'm not going to tell you it's STP. You have to figure that out. You have to figure that out. Let's take a look at this problem right here. Okay, how many moles of gas, of xenon gas in 2 liter, volume is 0 degrees and pressure is 1. That's STP. STP, standard temperature pressure. So we can do this and solve for moles, plugging in all these variables, or we can just do this. We've got 2 liters, and I know that at STP, for every 1 mole of gas, I have 22.4 liters. And now I have my new I can calculate the moles. Okay, I can calculate the moles. And when I do that, notice it's super easy. We're back to dimensional analysis. You're going to get this right here. Let me clean this up. (8.93 times 10 minus 2). Now you should recognize this number because this number was the same number that we had back here in that first problem I solved. In this first problem I solved right here. Okay. Sorry. We made quite a progress. That one right there. In this one right here, we used that and we got this value right here, 8.93 times 10 to the minus 2. But that's using PV equals nRT. But if we had recognized that this was STP, then we could have done the shortcut. Okay, could have done the shortcut. And gotten that in one step. So that's important, okay, using the ideal gas law. So that's basically how this was solved. Now there's a relationship. I'm switching gears on you. There's a relationship. If you have a gas, it's in a container, okay, then that gas in that container is going to have mass and it's going to have volume. What is mass over volume? That's a density. That gas in that container has a certain mass and it has a certain moles. What is mass over moles? That's a specific molar mass. Grams over moles, okay? So we can actually calculate the density and the molar mass of a gas using the ideal gas law. Let's take a look at the ideal gas law. PV equals nRT, okay? N is right here. We can solve for moles using this, PV over RT equals N. Now, if we weight that gas, if we calculate the mass or we weight that, then M over N is just M over PV over RT. You don't have to derive this equation, but I want to show you that it comes from the ideal gas law, or the mass, or M. What we can do is solve for N here, okay, grams per mole. And when we do that, what happens is I'm going to put this upstairs, put this downstairs, and put this upstairs. When I do that, I have PV over RT all over M. That's N. Now I can clean this up and write this. Or, like I said, that right there is the molar mass. So the molar mass equals M over PV times RT. That basically is the equation I want. And that's what you see right here. That's what you see right here. Sorry. There it is. So this right here is the molecular weight. The formula weight, molecular weight, molar mass is just the sum of the mass of the individual atoms that make up that molecule, like water, H2O. The molar mass of that is hydrogen is 1. There's 2 of them, so that's 2. Oxygen is 16. So 2 plus 16, that's 18.0 grams per mole. You guys know that from stoichiometry. That's how you would that's the equation you would use if you have a gas. Okay, and you are actually trying to measure out the temperature, pressure, and the volume, and you want to identify the gas. That's it. The density is just the mass over the volume. So we can take this right here and solve for V and then stick it in here. And now we would be able to solve the density. And so that's basically this right here. Let me clean this up for you. So this is the, oops. This is the density equation. That's the molar mass equation. You don't have to derive it, just know how to use it. Just know how to use it, okay? So here's a question. What is the molar mass of, you have a mass of 3.54 grams, and the temperature is 25 degrees. The pressure is 1.56 atmosphere, and the volume is 1.74. Remember that the molar mass, capital M, is equal to, let's take a look at that equation again, mass RT PV, RT PV. So we can do that, mass RT PV. So we do have the pressure, that's 1.56. We do have the volume, that's 1.74. R is 0.08206. Mass is 3.54. And the temperature is 298. Plug that in, you get the molar mass of the gas. So that's what you see right here. And you get 31.9. 31.9 is very close to 32. Oxygen, O2, is 32 grams per mole. This is probably oxygen, the molecule. Okay, that's oxygen, the molecule. So what's the density of that gas? Again, you can just plug it in and you can get that value. It's 2.03 grams. Remember that density when we're talking about liquids is grams per milliliter. Grams per milliliter. When we're talking about gas, it's grams per liter. Liter, not milliliters, because the density of a gas is so small, we need a bigger volume to get some good numbers. Okay, so the density is grams per liter, not grams per milliliter. So keep that in mind. That's the, so that pretty much summarizes how you would approach gas law problems. The last thing I want to talk to you about, and this is just a summary, because I want to make sure that you guys understand how to use stoichiometry in gas laws. So I'm going to close this real quick. Gas laws using stoichiometry. So let's take a look at this. And I won't go deeply into it, but what I do want to show you is this right here. This is the stoichiometry map. And in chapter 7, we basically dealt with this part of the map. We only dealt with the top portion of the map. Now that we are dealing with gas, okay, now that we are dealing with gas, we're also going to include this part. And whenever you can calculate moles, you can do stoichiometry. Remember, in PV equals nRT, that right there is moles. So that means that we can calculate the moles of gas when it's in a chemical reaction, figure out the stoichiometric ratio, get the moles of the gas as a product, and then use PV equals nRT to either determine its pressure or determine its volume. We can do that. So here's a, I'll do this particular problem and I'll stop there because I've been going at this for about an hour. Xenon will react with fluorine according to the following reaction. Xenon plus fluorine gives you xenon fluoride. Yeah, xenon's a noble gas, but heavy noble gas that are large, can actually do some chemistry. If a 2 liters of xenon gas at 0 degrees, 1 atmosphere reacts with excess fluorine. So again, this is the reaction, xenon plus fluorine. Fluorine's in excess, so that's not the limiting agent. It's going to give you xenon fluoride. Okay. How much xenon fluoride is produced? So we're given this unlimited amount of this. What is the mass of that? This reaction is a 1:1:1 ratio. So what first thing that we need to do is figure out the moles of xenon. Why? Because if we know the moles of xenon, then we can calculate the moles of xenon difluoride. And then if we know the moles of xenon difluoride, we can calculate the mass of xenon difluoride. So how do we get the moles from the gas laws? Sorry, this is the gas law, so down here, not up there. We use PV equals nRT. We use PV equals nRT. So 2 liters, 0 degrees, 1 as, hey, STP. STP. What we're going to do is do a shortcut. 22.4 liters equals 1 mole. We're going to use that as a conversion factor. So we have 2 liters, and we know that 22.4 liters is 1 mole. Now we can calculate the moles of xenon, and that's going to be, I think, 8.9 times 10 to the minus 2 or 10 to the minus 3, okay? And then we're going to use this stoichiometry map right here, okay? So we can do PV equals NR3, NRT, or we can use this right here. Now that we have the moles, then we can use stoichiometry. We know that for every 1 mole of xenon that is used, we produce 1 mole of xenon difluoride. The molar mass of xenon difluoride is 169.3. So when we do this dimensional analysis, the moles of xenon will cancel, the moles of xenon difluoride will cancel. We get the mass of xenon fluoride. That's the stoichiometry. So when you're dealing with stoichiometry, okay, use this to get moles. Once you have that, then we're back in chapter 7. I'll do this last example and then we'll call it quits because I have, I think, another review for lab at 6 o'clock. So let's take a look at this example right here, okay? This example is, I have 1.33 grams of zinc. I'm gonna react it with excess sulfuric acid. I produce zinc sulfate and hydrogen gas. So hydrogen, the gas is my product. And I'm starting with the mass of a solid. So the mass of a solid is right here. That would be your zinc. We can get the moles of zinc using the atomic weight of zinc. We can use the balance equation to get the moles of hydrogen. And then we can use PV equals nRT to get the, what are we trying to get? The volume of hydrogen. So we're going from this portion of the stoichiometry map to that portion. It looks like that. And this is your approach. Take 1.33 grams of zinc. You know that the atomic weight of zinc is, I believe, 65. Okay, 65.41. Then, according to the balance equation, let's make sure this is balanced. It's a 1:1:1 ratio. 1 mole of zinc sulfate produces 1 mole of hydrogen gas. And I want to stop there. I need to stop at moles because then I need to convert from dimensional analysis to PV equals nRT. So when I do that, I get 0.0203 moles of hydrogen gas. Let me clean this up, okay? Now I can use PV equals nRT. Remember that I'm solving for V. So V is equal to nRT over P. I know my moles, I know my T. and I know my P. Here, you need to convert torrs to atmosphere because we're using R. Whenever you're using R, you got to use atmosphere. So this problem becomes 0.0203 moles, okay, 0.08206 liters atmosphere, mole Kelvin. So that's 0.08206. Temperature is 293, and the pressure is 0.97. That's how I would solve for volume in this particular case. Let me clean this up so that I can show you that. Okay, this is it right here. And we get 443 milliliters or 0.443 liters. If you multiply that by 1,000, you get milliliters. Okay, so those are examples of how you use gas laws in stoichiometry problems. This is it right here. You need to calculate moles. Okay, so hopefully that gives you a overview of chapter 8. It's pretty much mostly about PV equals nRT. Pretty much about PV equals nRT. Make sure you understand how to use that. Okay, but that pretty much is it in terms of this discussion. If you have questions, let me know. You can send me an email, but practice the problems. The problems can be intimidating because you have a lot of numbers, and I know a lot of you hate numbers, hate math, but dive into it and break it down, simplify the problem. Look at the problem, look at what you're given, define what your volume, your pressure, your moles, your temperatures are, figure out what is being asked, put a question mark on that variable, and see whether it's just a condition 1 problem, a condition 1, condition 2 problem, or there's actually a reaction, a chemical reaction involved, in which case you have to attack it using this stoichiometry map.